Hello everyone. Right now, let us have the case study. Study on pulse saving for cellular digit packet data over a random error or loss channel. I'm Huei-Wen Ferng. Well, this is the outline. We'll have introduction, pulse saving mechanism design for CDPD, and the new design by using combination of selective repeat ARQ and pulse saving mechanism. And of course, for the current article, we have numerical result and discussions. And finally, we will have the conclusion. And for your term project, in fact, you can have the paper and also you have the outline. For example, here we have introduction, pulse saving mechanism, combination of the schemes, and finally the numerical result and discussion. So you can follow some outline like this. First of all, we have introduction. CDPD. CDPD is a data network overlay over the first generation cellular system called AMS, Advanced Mobile Phone System, AMS. For CDPD, we have elements of mobile end system, mobile data base station, mobile data intermediate system. Well, MES, it is the user end terminal. Alright, and mobile data base station. Base station here, so was analogous to the normal base station in AMS. As for mobile data intermediate system, it works like the mobility management, routing, and allow routing to the other mobile intermediate systems. Here we have for the architecture of CDPD. We have MES connected to base station, and base station connected to mobile data intermediate system through wire line. And actually, mobile data intermediate system can be connected to the other mobile data intermediate system or the external network. Well, MES and MDIS later. We will emphasize the pair MES and MDIS later for the design. Well, first of all, let us check the pulse saving mechanism in CDPD. To have the pulse saving mechanism, usually we can have timers. And we will employ two timers in CDPD. First of all, we call T203, and the next one is called T204. T203, it is called element in activity timer. As for T204, it is called TEI. TEI later we have a TEI notification timer. Well, for MES, it can trigger a T203 timer when it completes a frame transmission. That says finish the transmission of a frame, then it can trigger this timer, T203 timer. And actually the timer will reach timeout. Reach timeout means counts down to 0. And the server reach timeout, and then we can have the other mechanism. But right now we need to count when we can reach 0, reach the timeout. And for the timer should be reset. When we should reset? When data frame require MES to receive or send before it expires. You see, expires. Well, of course, we have a timeout that says timer expires. And then timer expires here. Timer expires, then MES enters the sleep mode. Alright, so we can have a T203 to count to 0. Once we reach 0, it says timer expires, and then MES enters the sleep mode. To wake up the sleeping MES, we have another timer, and this timer called T204. T204 is maintained and periodically triggered by the MDIS for each channel stream. Well, if we have this timer, actually the timer can be expired. I can reach timeout, and MDIS broadcasts a frame containing TEI. TEI actually containing some station within serving as the TEI, and with a pending frame to be delivered, but queued in the buffer at the MDIS. So that says containing TEI means we have the list of equipment, and these are for equipment to receive the pending frames. Well, if we have a T204 timer expire, and then all MES wake up to listen to the broadcast message during the broadcast period. Well, because of TEI and TEI for a specific MES can be found. If it can be found, then the MES need to leave the sleep mode. So TEI is a list containing a specific one, and then that specific one need to leave the sleep mode. Well, after leaving the sleep mode, then MES send a receiver ready frame to the MDIS and allow the MDIS know right now this MES is ready to receive the pending frames. Well, this is the frame sent by MES. However, if we don't have the RR frame received by the MDIS, then it seems to be nothing filled by MDIS. So MDIS will trigger another T204 timer. So this is the situation if one MES is included in the TEI. And actually, how about MES is not included in the TEI? Then nothing to do. So nothing to do, then this MES can remain in the sleep mode. So if we cannot have the list of this MES in this TEI, and then that MES can remain in the sleep mode. Here we have the simple mechanism. We will trigger the T203 timer. Right? Alright, triggered by this MES. And another one, TEI notification and received by MES. MES need to check should this one included in this MES. If yes, then it need to wake up, or otherwise it can remain in the sleep mode. Well, now we need to have the design of the combination of selective repeat ARQ and the previously stated PSM. Put them together. So what is the performance? And how to have the proper design for this combination. First of all, we have events and action for MDIS. Because we focus on the pair, MES and the MDIS. So we ignore any other interactions for MDBS, mobile data base station. So first of all, it's possible to have arrival of data frame from other MDIS or network. If so, arriving, therefore, when we put this frame into the buffer, if we have the available space, or otherwise not available space, so we need to discard the overflow frames. If T203 timer for the MES does not expire, then we can deliver frame. Okay, and to deliver the frame, we need to associate a frame timer. It is called frame timer. The timer associated with this frame, so we call frame timer. All right, and also we have the window. So we have a sending window. The sending window will be maintained. If we still have available space within the sending window, then we can send the frame further. And next one, arrival of a data frame from an MES. And if so, arrival, right, we trigger the corresponding T203 timer and check frame is necessary to be retransmitted or not. If yes, then we need to send NAC. All right, retransmit, so we need to send a NAC. Now, okay, so we send NAC, or otherwise send NAC and check whether sequence number is within the receiver window. Why? Because we need to send the frame within the window. If not, then we need to discard the frame. And the timer of a T203 timer will broadcast, because timer for this type of server, we need to broadcast a TI notification frame. And this frame includes all sleeping TIs to all mobile and equipment and system. Well, so timeout, and then we can trigger another one. So we can trigger T204 timer again. As for the other design, we can have timeout of the T203 timer. All right, timeout, then go to sleep mode, so we can set the status to sleeping. And timeout of a frame timer. Then frame timer is maintained to control the retransmission, so we need to resend the frame. And of course, resend it, we need to set the timer again. And how about receipt of ready to send? If so, ready to send, then we can trigger the corresponding T203 timer and deliver frame queue in the buffer, of course with the sequence number. Well, next one, it is receipt of an ACK on NAC. All right, so receive a NAC on NAC, then we trigger corresponding T203 timer. And if this is an ACK, all right, so ACK, we need to remove frame in queue smaller than the sequence number, because everything's done. If it is NAC, then we need to resend the expected frame or frames. All right, so with ACK and NAC, and later we can deliver further. So deliver affordable frames. All right, because we can deliver affordable frame, we need to set frame timers. Well, likewise, we can have the design for the events and action for MES. And let me skip some details and let you know. We can have arrival of a data frame from the MDIS and the others. Well, for this one, actually we can have the simulation to investigate the performance. So here we have the simulation modeling and assumptions. We focus on one MDIS and MES pair. And the data frame for an MES are generated by a Poisson process. And how about the batch size? The batch size is set to the uniform distributed number of frames. And we have errors or losses. Actually, error or losses are modeled by Bernoulli random variables. And here we don't have error correcting code. And the timer set to the frame timer, it is 0.1 seconds. And T203 we set it to 30 seconds. And T204 we set it to 60 seconds. As for buffer size, it can be 10 or 30. 10 or 30 times of data frames. And later about the performance measure, we will measure drop-in probability, sleeping ratio, and waiting time. And in fact, we won't show waiting time in the following slides. So first of all, sleeping ratio. By checking different window size, it says, well, almost the same, right? Comparable sleep ratio for the current window size. How to have the setting? We set BR to 0.01, frame loss probability to 0, and here we investigate buffer at 10. And we know selective repeat ARQ window size actually affects little to the power saving mechanism because we have a comparable performance. We then set window size to 4 for the investigation. So set it to 4 simply. And about drop-in probability, because of the limited size of a buffer, we will have a drop-in probability. And right now we have error-free and the other values of bit error rate to investigate the drop-in probability. We can find maybe we don't have the same trend, but you can see when we have a BR greater than 0.01, this setting results in performance deviation. All right, so this is the first point we need to point out. And that says, okay, so here we can see general condition was and saw that BR greater than this one. So was enough, and then retransmission turns into the main burden. And so of course we have the high drop-in probability. And this one, sleep ratio again, we have different buffer and same set value to the buffer size, then we can have the comparable sleep ratios. And how about size 10 and size 30? We can see size 10, then we can have a high ratio, but size 30, set 30 to the buffer size, actually we have a low sleeping ratio. Here we can have the observations. Increase of both BR and the buffer size will cause sleeping ratio to drop down. All right, and actually we can choose one BR equal to 0.0001 is gain, and then half the ratio. All right, when we use BR equal to 0.01. Well, how about this one? Actually, we have from loss probability. Maybe not the same as DR, but we can find when we exceed the different arrival rate, and then we have the observable probability dropping probabilities. Well, this is conclusion. Within the conclusion, we have the system performance investigation, and system performance is insensitive. Look at this, insensitive to the window size finally we set 4, and we have a selective repeat ARQ, and actually if we have the channel condition BR higher than or equal to 0.01, then we have the observable large loss probability. All right, and when BR lower than the value here, or firm loss probability lower than 0.1, sleeping ratio of an MES then affected little. Alright, affected little. Well, after now it says we have the performance investigation, and then we will have the proper setting for the selective repeat ARQ, and so that we can have the performance enhancement. Alright, that's all. This is the case study to this article. Alright, power saving mechanism of CDPD, and of course we want to work with the selective repeat ARQ. Alright, that's all. Because of online delivery, so this time I won't ask you any questions. Just serve as the illustration of the content of this article for you. If you need to check more, you can refer to the paper. Alright, that's it, and thank you.